Okay, this is going to be a walkthrough of the midterm. And then next time we get together for Zoom, you can ask me any questions, but I thought I'd post a video so you can kind of think through the answers on your own time, and then we'll ask questions after that. Okay, so I'm going to go through the problems one at a time. I'll start with number one here. And this is the table where you were asked to show me the register contents and memory contents after every instruction was executed. And as you can see here, I gave you initial values for registers and for some memory locations up on top. And then as we proceed through here, there'll be, I guess, kind of two components. One is that we'll modify register contents and memory contents with some of the instructions, but the other is that there's some write back happening. Like this instruction here, we're going to add a value to a base register and write it back, and same with these guys down here. So that's part of the problem as well. Well, let's just start with the first one. So this says move to the top of the word of R4 and FFF0. So R4 here contains all F's, so I'm going to put an FFF0 in the top. And if this is kind of messy, I'm going to show you a typewritten one at the very end. So I'll try to write neatly and explain as I go. But again, I'll show you the actual key here at the end with it all nice and typewritten so you can look at it better. Anyway, FFF0 and then FFFF is in the rest of the register. So the first instruction, all it's going to do is just put FFF0 in the top 16 bits of R4, nothing else. Next one says, let's rotate right R4 by 16. So I'm going to take the lower 16 bits, wrap them around to the top, and move the lower 16 bits down to the bottom. So that's going to give me FFFF. There's the lower 16 bits rotated around, and then FFF0. And that's all that instruction is going to do. Okay, the next one, load register 3 from an address pointed at by register 2, and here's register 2's contents up here, 101,000. I want to load register 3 from that location, and that's the address, so I'm going to look over here at that address. That's the address that's in R2. Well, that's the number that's in R2, and I'm treating it as an address because of those square brackets. And I'm going to load the contents of that memory location into R3. So that contains an F. So an F is going to get loaded into R3 because of that instruction. But then I can see I'm doing a post modification and I'm writing it back. So R2 now is going to contain R2 plus 4. So in the same exact instruction then, I'm going to copy the contents of R2, 0, 0, 1, 0, 1, 0, 0, but now I'm going to add 4 to it. So 1, 0, 0, 4. This instruction also modifies the base register, which is R2. Okay, and that's it for that one. Now I'm going to add into R4. So currently R4 contains a bunch of F's. I'm going to add into R4 again, plus R3. And now R3 contains an F. So R4 gets R4, which is all F's, plus R3. So if I add one more F, and that F is in the least significant 4 bits of R3, I guess I could have shown, 7 zeros and an F. But I'm adding this single F into that register that contains all F's except for the lower 4 bits. So the effect of that is going to be to put all F's into R4. F, 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 F. So R4 contains all F's. And that's all that happens with that instruction. Okay, the next one now, I want to store all of those F's at the address pointed to by R2. So now R2 contains 00101004. So I'm going to come over here and I'm going to write that address down. I'm going to say at address 001 01004, because that's the address I'm going to refer to, I'm going to store the contents of R4. And R4 contains all F's. So I'm going to put F, 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 F at that location. And that's what that instruction does. Okay, next one, I'm going to add a 1 to R4 and store the results in R0. Add a 1 to R4, so R4 contains all F's. All F's plus a 1 is going to be right back to 0. So the results of this is going to be, again, all F's, all 1s, plus 1 is going to roll back the contents to all 0, and that's going to get stuck over here in R0 because that's the destination address. So again, that number results from adding 1 to all 1s, or all F's. And that's all that happens there. No other contents are modified. Okay, this next instruction says store R0, the contents of R0, which are now all zeros, right? Store the content of R0 at an address formed by combining R2 and subtracting from that R1. So now R2 contains, where are we at here? That address, 00101004, and from that I'm going to subtract a 4. So I'm going to put something at an address. I'm going to store at that address. So let's first write the address down, 00101000, right? Because I'm subtracting a 4 in R4 from R2. That's what that says. And at that location, I'm going to store the content of R0, and that's all zeros. 2, 3, 4, 1, 2, 3, 4. But I'm not done yet, because that exclamation point says when you're done with that, then update the base register R2 with the address you just used. That's what the exclamation point means. So into R2, the base address goes the address I just used, 0010001000. Okay, last instruction now says store the contents at R1, which is a 4. So I'm going to store R1 somewhere. Where I'm going to store it is made up of that expression there. So I'm going to add to R2. R2 currently contains 00101000. I'm going to add to that R1, but before I add R1, I'm going to logically shift it left by 1 bit. That's going to turn the 4 into an 8. So I'm going to add to this base address an 8. So over here then, that address is going to be 00101008. That's the address I'm writing to. And I'm going to store the contents of R1 there. That's a 4. I'm just going to write a 4 there. And once again, that exclamation point says when you're done doing the operation, then update the base register R2 with the address you just used. So that's going to be 00101008. And that's what I was looking for there. And all of those are worth 2 points each. And then, as promised, let me put this up here so you can kind of see a better version of it for a little bit. And I'll leave that there for a few moments. And while that's there, I don't have the averages of each problem computed yet, but I think there were 28 points possible on this problem. And I think the average on this is going to turn out to be 16 or 17 or 18, somewhere in there. So if you want to stare at this for a moment, you can pause the video. And other than that, let's press on to the next problem. Okay, problem 2, kind of similar, but this was more focusing, I think, on the condition codes, the bits coming out of the ALU. But I still wanted you to track through the register changes to give context for what's happening with the condition code bits. But kind of the same idea. So initial conditions and then the instructions. Let's work through them. So move to the top of R2 a C0000. So I'm going to modify R2 with this instruction, and in the top I'm going to put C000, and then the bottom is going to stay the same. So that would be the register content after that instruction. How about the status bits out here? I don't know if you remember, but a move instruction, especially move top instruction, won't change the status bits. So we really don't know what they're going to be, whatever they were. So it didn't matter what you put there. I didn't even look at them. I didn't take off credit or add credit, so they were kind of a don't care for that instruction. Okay, the next instruction, logical shift right R2 by 1 and put the contents into R1. So R1's getting a new value, and it's going to be R2, which now contains C and a bunch of zeros. I'm going to shift that right by 1 bit. So that's going to put into R1 then a C shifted right by 1 bit, and that's going to give me a 6. If you're not sure about that, you can write it down and look at the bit patterns. Okay, now a logical shift can affect the status bits, but there's no S there, so it doesn't affect them. So once again, we have no knowledge of what those bits are going to be. And so I couldn't grade that either, so I didn't grade in any way the status bits in that line either. Okay, the next instruction. Add into R3 the contents of R1 plus the contents of R2. So what's that going to look like? Well, R1 contains a C000, so R1 is going to contain a 1, 1, 0, 0, and a bunch of bits. R2 is going to contain a 0, 1, sorry, R1 is going to contain a 0, 1, 1, R2, R1, and I'm adding those together to put them in R3. So these bits are all going to be 0, the lower bits. So I'm going to get 0, 0 plus 1 is 1, and then 1 plus 1 is 0, carry the 1, 1 plus 1 is 0, carry the 1. So I'm going to get that, this is bit 31 here, and counting on down from there. So that's going to give me a 2 in the upper part of R3, followed by a bunch of zeros. So right here then, I'm going to get 2, 0, 0, 0, 0, 0, 0, 0. And that's the only register that's changed by that instruction. Now there's an S on the end of the mnemonic, so I am going to update the condition code bits. So that result is not negative. Notice that the most significant bit there is a 0. It's not a 1. So it's not negative, so that's going to be 0. It's not 0, so that's going to be 0. I did get a carry out. I carried out that 1 right there. Got a carry out. So that's going to be a 1. And the result is arithmetically, I combined a positive and negative number, so that's going to be fine. That's not going to be I'm not going to get the V flag set. So that's the first time the status bits had any meaning. Okay, next instruction. Subtract R3 from R3, and somebody pointed out I had an uppercase and a lowercase, but it doesn't matter. It's R3 in both cases. So I'm going to subtract R3 from R3. I'm going to subtract a number with a 2 in the upper bit from itself, and that, of course, is going to result in 0. So R1, when I subtract one number from itself, I'm going to get all zeros here, all zeros, and then I'll update the condition codes. So the leading bit is not a 1, it's a 0, so it's not a negative number, but it is 0. And now, did I have a carry flag or not? That's a question. Well, if you actually do the subtraction and carry it out in a formal subtractive sense, here, 0, 0, 1, 0, some dots, 0, 0, 1, 0, some dots. You could think about it as you could make that a 2's complement number and do the addition. Maybe that's the best way to see it. So I'd have a 1, 1, 0, 1, 1, 1, and then see if a carry flag results, or I could just do the subtraction. And either way you did it, you'd find that there is a carry flag. Now, if you're not sure about this, I was hoping, maybe thinking that what you might do is put that into Vitus and run that particular instruction and then go look at the status bits. And if you did that, you'd see that the carry bit is in fact set. But there's also no error. Subtracting a number from itself doesn't result in an error. Okay, then I'm going to logically shift right R2 by 1. And this instruction, it's an abbreviation. And again, if you weren't sure, you could type it into the assembler or to the Vitus tool. But it says take the value in R2 and shift the value in R2 by 1 and put it back in R2. So just like before, I'm going to take a C and I'm going to shift it into a 6. Status flags, no S, they stay the same. There's the status flags. All right, now I'm going to add into R1. So I'm going to change R1. I know that's getting a new value. And I'm going to add R2 plus R3. So I'm going to add R2, which contains in the upper bits a 6, a bunch of bits, plus R3, which contains a 2 and a bunch of bits. So when I add those, I'm going to get 0. 1 plus 1 is 0, carry the 1. 1 plus 1 is 0, carry the 1, 1, and a bunch of bits. So I'm going to get here then, I'll write that down, that's an 8. That's the only register that changes. But now I've got the most significant bit set. Bit 31 is set. And that makes that a negative number. So that's going to set that flag. It's not 0. There was no carry out, you can see. There was nothing to carry out of that most significant bit. And now, because the sign bit flipped, the V bit is determined by the XOR of the carry in and the XOR of the carry out. And that's going to give me a 1. So what I did is I added 2 positive numbers and I got a negative number. And that's what the V bit is there to tell you. And that's why it's set to a 1. Okay, and then lastly, I'm adding, and the S bit was set, I guess I said that already. I'm adding into R3, so now R3 is going to get a new value. I'm adding R1 plus R1. So R1 contains a 1 in the most significant bit. All right, so when I add that to another copy of itself, I'm going to get all zeros. 1 plus 1 is 0. I'm going to carry out a 1. So now the number here in R3 is going to be all zeros because the most significant bit got carried out. Okay, so when I do that now, that number is no longer negative. It's positive because the leading bit's a 1, so it's not negative. It is 0. There was a carry out. You can see right there, there's the carry out bit. When I added 1 plus 1, I got a carry out of 1. So that gets set. And again, I combined 2 negative numbers and got a positive. So that is also going to be a condition for setting the V flag. Again, I XOR the carry in to the carry out of the most significant bit. And then what I was getting at for number 3 here is that because the V bit is set for these 2 instructions, 6 and 7, those answers aren't correct. Now I suspect that you're going to yell at me for not really understanding what I was asking there, because a lot of people got this right, but a lot of people got this wrong as well. But that's what I was going for, the fact that the numbers resulting from the instructions 6 and 7 are incorrect. And they're incorrect because we only have 32 bits to represent information, and we combine numbers in such a way that they were no longer accurate. And just like before, let me put this up here so you can see the results typed, and I'll leave that there for a second. Kind of soak that in. And I guess you can stop the video if you want to have more time to look at those. Okay, I'm just going to leave this up here because pretty much the entire class got this right. I think all this was is an exercise in can you type in these numbers into Google and get the right results. But everybody did, so I guess you either know how to convert the numbers or you certainly know how to type in bases into a search engine or a calculator and get the right numbers back out. So that was kind of a perfunctory problem, and again, I think everybody got all credit on that. Okay, let's move on to the true-false section, which we already did. And then a bunch of you sent me your comments on certain problems, and I think I, in every case, agreed with everybody that wrote and gave you the points back. So we've already done this. If you're not familiar or you missed the last lecture, you can go back and look at the recording. Let me see if I've got a key I can put up here just in case. Where did I put that? Well, I'll just draw it on here real quick. So let's see. This one was true. There weren't most of them were false. So that one was true, and then that's true. That's true. And then what's the next one? That's true. That's true. And I guess it's maybe it goes without saying, if I'm not marking them as true, they're false. That's true. That's true. And what's the last one? The one all the way down here, second from the bottom, was the last one that's true, that one. Everything else is false. So again, if you want to write me an email in support of a different answer than I got, do that here in the next day or two, and I'll take a look at that. Okay, and again, we went over that in the last class. Okay, moving on. So this first one was just to make sure that you could decompose a relatively straightforward computing operation into ARM assembly. So I kind of said minimum number of ARM assembly instructions here. So the idea is you could do this in 3 instructions, and there were a couple of ways to do it, but maybe a good way. Oh, and I told you that the operands are in R1, R2, and R3, and R4. So a good way to do it would be to say add into R1 the contents of, R0, into R, I'm going to use R0 as an accumulator. Into the contents, into R0, I'm going to add R1 and R2. And really, I suppose I could have used R1 there as well, and it wouldn't have affected anything, because once I've added it in, I don't need that value anymore. So could have been R1. And then into that accumulating total of R0, I'm going to go ahead and add the next operand, which is R3. But I want to add it to the accumulating total in R0, so I'm going to add back in there R0 and R3. So at the end of those 2 instructions, then I've done that much. I've added the first 3 operands, and now the sum is in R0. And then the last thing I want to do is subtract from those. I want to subtract R4. So from R0, into R0, I want to put the result of subtracting R4 from R0. So just those 3 instructions are all I was looking for, or the equivalent. And you got 3 points per instruction for a total of 9 points. Now, same idea here, but there was a little twist in that that's why I wrote minimum number here, because if you understood the conditional execution, you could do this also in 3 instructions. So again, lots of ways to do it. One way to do it would be to say add into, again, I'll use R0, the sum of R1 and R2, right? Because that's A was in R1 and B was in R2. And then I'm going to do the same thing, but I'm going to add into another register. I'll pick on R3. I'm going to add into R3 R3 plus R4. I had to think there for a second. So into there, I'm going to add R3 plus R4, and I'm using so R3 contains the C operand, but I don't need it anymore for this computation, so I can add R3 back into R3 plus R4. And now if I say, go ahead and set the condition code bits, now the result of that instruction will tell me whether or not it equaled 0. And this instruction here, this last one in this pseudo C, I guess it is C, says if y is not 0, then add those two together. Well, the flags are now set. So now I can say add, if it's not equal to 0, add NE. R0, R0, and R3. So in just 3 instructions then I can do everything there by using the conditional assembly. So this add will not happen if the result of this previous instruction was not 0. Okay, then you had to go and put the condition codes, you had to come up with the opcodes for that. Now the best way to do that would have been to type this into Vitis and go look at the disassembled code, and you could just type it in directly. If you didn't do that, then you would have had to have figured out the opcodes, and that's not impossible. You could do that as well. And either way, you'd come up with the opcodes. So for my instructions, the opcodes for those 3 instructions was E081. And if you go look, E, that's 1110. That's the always execute command. So there's no, this is not, these two are not conditional, so they both start with E. And this one, because it is conditional, you'd have to go look at the condition code, but the condition code for NE is 1, so that opcode starts with a 1. But let me finish up this first opcode. So E801 and then 0002, that was my opcode for that instruction. E093 3004 was the opcode for that instruction. And then for the add not equal, that opcode was 104 00003. And admittedly, I didn't trust myself, so I just typed those into Vitis and then looked at the disassembled version of it and pulled those opcodes directly from Vitis. So that would be a good way to make sure you didn't make any mistakes. Okay, the last 2 problems, I think those are the last 2 problems, right, were programming problems. Yeah. And so there's lots of ways to solve these problems. And so what I did is I typed up a couple of them and printed them out, and I thought I'd talk through them. And again, if your code isn't identical but does the same thing, that's just fine. So for number 7, here's what I came up with. So the important parts are that, so this is the one where you had to add up consecutive numbers in memory. And let's see, just read it here to refresh ourselves here. Write an assembly program to add values stored at consecutive locations starting at label X data, and I gave you that in the code, and continuing through a value that's given to you in R0. So in the for loop, I use J here, but then I said that's given to you in R0. So you already had that value supplied in R0. All right, so that was given, right, that much. So we needed a couple of things. We needed an accumulator. So I cleared one of the registers using a BIC instruction to be my accumulator. And then you have to load the address, the start address, into a register. I chose R1, so I'm using the sudo command load register R1 with equals X data. So now I have the address in R1. Okay, then in my loop, I'm going to load R3 from that location. So whatever's stored at that address is now going to be in R3. And then after I do the load, I'm going to add 4 to the address. So now there's going to be a 4 in the least significant nibble there. And that will be the address of the next operator. Because remember, addresses are in bytes. And we're doing 32-bit accesses, so I need to add 4 bytes, number 4, to get to the next consecutive address in memory. That's why that's a 4. So again, after this instruction, R3 will contain the first data element, and the R1 address will be that plus 4. Okay. Then I'm going to add that data element in R3. I'm going to add it into R2. Remember, I cleared R2. So R2 is going to get itself, which is 0, plus R3. So the first accumulated data element is now in R2. Then I'm going to subtract from R0, and remember R0 was given to me as a parameter telling me how many times or how many locations I'm supposed to add. So I'm just going to decrement that, and if it's not 0 yet, I'm going to go back and do it again. And so I'm just going to stay in that loop, adding 4 to the address every time, getting that next data element and adding it into my accumulator until I've gone through the entire loop value, and again the loop value is stored in R0. So different ways you could have done it. This is one way, pretty clean, pretty straightforward. So that's what I did. Leave it there for a quick second. You can stop the video, I guess, if you want to look at it some more. Okay, then the next problem, final problem. Write an assembly routine to count the number of ones in a 32-bit data element. Your main program should read the data from an address I gave you and then pass that as a parameter in R0. Okay, then you're supposed to assume you might call another subroutine, and that's important for context saving and restoring. Preserve context. A lot of people did not preserve context. In fact, some people didn't even write a subroutine. Supposed to write a subroutine and preserve context. Those are some key words there. Return the number in R1, and then if you want extra credit, you could modify your code, and a couple people did this, modify your code to pass the value on the stack instead of in a register. Okay, so once again, I printed out a couple of ways to do that. Here's one way, not using the stack. And you didn't have to do it this way. This is just a way that occurred to me, pretty simple and straightforward. So again, I gave you this much code up here. I gave you the kind of the starting stuff, but you had to write a main program because you were supposed to call the subroutine from the main program. So that's what's happening here. And the main program just had 3 instructions and then an infinite loop. So the first thing I did is I loaded the location of the data using the pseudo instruction into R1. And then I put the actual data, so that's the address now in R1, put the contents of that address into R0, and then I went to my subroutine, and that's it for the main program. In the subroutine, then the first thing I'm doing is saving context. And I didn't have to use R5 and R6, I just did it just to give you some more example of saving context. And so notice the first instruction is I'm saving context, I'm saving R5 and R6 because I use them, and I'm supposed to restore them afterwards. I could have used R0, 1, 2, or 3 and not saved them, but I, again, did this to illustrate a point. And the link register. And then down here, the last thing I do is I restore them before I branch back to the main routine. So that these two instructions here, the push and the pop, bracket my subroutine. And that's pretty common to see the push and the pop being the first and the last instruction of a subroutine, preserving and restoring context. Okay. Then I'm going to put the loop count. I know I need to do this 32 times because it's a 32-bit location, and I want to count the ones in a 32-bit location. So into R5, I'm putting the number 32. That's going to be my loop index. I'm clearing R1. R1 is going to be the accumulated total of ones, so I can use that to count. And then I get into my loop, and my loop's just these 4 instructions here. So the first thing I'm going to do is AND R0. Now remember, R0's got the data. I'm ANDing it with a 1. So that means that R6 is either going to contain a 1 or a 0. It's going to contain a 1 if the least significant bit of R0 was a 1, then R6 contains a 1. If the least significant bit of R0 was a 0, R6 contains a 0. So now I can add R6 into my accumulator, R1. So I'm going to add R1 to whatever was in R1 because it's an accumulator plus R6. And again, R6 is either a 0 or a 1. So if it was a 1, I'm going to add 1 to the total. Then I'm going to logically shift right R0 by 1 bit. A lot of people put logical shift left. You want to go right. I guess you could go left, but you'd have to have some other differences in your code. Shift it right by 1 bit. Update my loop counter. I'm going to decrement it by 1. and then branch up here again. So this is going to make sure I do the loop 32 times. That's all those last two instructions are doing. So every time through the loop, I'm going to AND R0 with a 1. So I'm going to just pick off the least significant bit. If it's a 1, well, it doesn't matter if it's a 1 or a 0. I'm going to add it into R1 and then shift again. So I'm just going to shift the bits out one at a time. And if they're a 1, they're going to contribute to the accumulating total in R1. And so by the end of 32 shifts, whatever's in R1 will tell me how many 1s were in that location. And then I restore context and go back to the main part of the routine. So that turned out to be pretty straightforward as well. I'll let that sit there for a second. And again, there were a bunch of, maybe a little thoughtless kind of errors people made. And I tried to give as much partial credit as I thought I could justify for this one. And then the last thing I want to show you is the exact same subroutine, but this time using the stack. And I think only three people attempted it, and a couple people made some small errors, so I didn't take anything off for that. I just didn't give you any extra credit. So here's what my solution for that looked like. Everything's the same. Well, I guess not everything's the same. The first thing I did up here is I pushed R1 on the stack. So I think that should have been R0. Typo there. So I put the data into R0, and that's what I want to put on the stack. So now I loaded the contents that I want to count the 1s in into R0, push that on the stack. Okay, so I come into my subroutine then, and the first thing I'm going to do is save the link register and frame pointer. And this is right out of the example code on the website. I'm going to move the stack pointer into the frame pointer so it now points just above my data. I'm going to save some more local registers. Again, I didn't need to do this. I just did it because I could. And then I'm going to go get the data. And again, right out, you can go look at the examples in the class write-up. But in my case, the data is 8 above the frame pointer. So I'm moving the data off the stack into R0. And then everything else is the same in here that we just went over. Everything's the same. But when I finish, then I need to do a couple of things. First, I got to restore context. So there's the push, there's the pop. Then I got to collapse the stack by moving the frame pointer back to the stack pointer. And then lastly, I'm going to restore the rest of the context and return. So there's a couple of variations on how to do that, but that's the one I chose. Okay, well, that's all I've got for this lecture. So again, look through your scores, and I think by comparing your scores and knowing what each problem's worth with what I've done here, if I took off points, I'm thinking you can probably figure out where you lost the points. If you have any questions, email me, or we can talk about it in the next lecture. And also, let me point out, for the next lecture, I've posted 2 lectures on interrupts. And those are the 2 lectures that are relevant for this point in the class. So watch both of those. One would count for, I guess, last Friday's lecture. If you haven't watched it, watch it. And one will count for this Wednesday's lecture. And then this, of course, lecture I'm just now doing would be for Monday. But I will join you on Zoom on Wednesday, and I'll primarily be there if you have questions on anything. So you don't need to come to the Zoom lecture on Wednesday if you don't have any questions, but if you do have questions, I will see you on Wednesday in Zoom. And of course, you can always email me at any time as well. Okay, that's it. We'll see you then. Bye-bye.